So we are now going to have the Laudatio for the third field medalist. Now, Ofer Zeitouni only found a spot way at the back, so we're waiting for him to march to the front. There he is, so that he can get the microphone.
Yes, I do need the remote control. He didn't give it to me then.
So Ofer will tell us about the work of Martin Heyer. Go ahead.
Okay. So it's a great pleasure and honor to present to you the work of Martin Heyer. Martin has made fundamental contributions to the theory of stochastic partial differential equations. He has developed, more or less single-handedly, a theory of regularity structures, and that is a construction of solutions to nonlinear, in general ill-posed in a sense I will explain to you, stochastic partial differential equations by local expansions and renormalization. Lots of words. I will try by the end of this presentation to make it clear what I mean here. In addition, and earlier, he has also developed a theory of ergodicity for infinite dimensional systems. In the presentation now, I will focus exclusively on his work on regularity structures. And I will try to show you how it fits both the world of partial differential equations and the world of stochasticity. But first, a brief mathematical biography. He was born in November '75. He got his PhD in physics with Ekman in Geneva, although physics is taken in a pretty mathematical sense in this case. He is currently a Regius Professor of Mathematics in Warwick University. In the last year, he has got many prizes and recognitions. In particular, he is now a Fellow of the Royal Society. Okay, so I decided that since I'm going to talk about stochastic partial differential equations, and since I guess that many of you have never heard of stochastic partial differential equations, I should give you a little bit of background. And the background starts really with differential equations. So those are objects that we all know. And as we know, the physical world is often described by differential equations, but as Etienne has pointed out, this is not really true. So one way around is to say that you do not know the function f. Another way around is to add noise to the equation. Those are divergent views of differential equations and how to fit them to the physical world. Now, the equations that you see in the display here is an example of such a model. The symbol nt actually describes the noise at time t. And of course, if we have noise in the system, then, and if we are modeling a real system, it should be the case that somehow if we approximate the noise by an approximate noise, the system we get should be similar in some sense to the system for different approximations. So it should be that there is some kind of continuity in the noise, and we will see that this will play a big role later. So this I write as a symbol that if you have a sequence of approximation nt epsilon that converge to nt, the solutions should converge in some sense. Now, a natural noise that people have played with is what is called white noise. So what does white noise mean? It just means uncorrelated in time. So there is no probabilistic, no correlation between the noise at different times. This is a very nice model. The only problem is that it doesn't make sense. You cannot construct a true stochastic process that has this property unless it degenerates to 0. However, the integral of such process can be made rigorous. This was first done in a non-mathematical context by Brown, a botanist, who actually observed it in the motion of pollen. In the turn of the century, it was first applied to what is considered the beginning of financial math by Bachelier, so to the motion of the stock market. We have heard a lot this morning about financial application of stochastic calculus, so it goes back to that period. Shortly after, Einstein and Shmulukhovsky gave applications to the kinetic theory of gases, but one had to wait a few decades for the mathematical foundation of the theory, which came through the work of Wiener and Levy. And what they showed, besides constructing these objects in a rigorous way, is that the path, you can give sense to the path, and a typical path of the Brownian motion, viewed as a function of time, is almost Holder 1/2. Okay. So what this means, if the path is almost Holder 1/2, surely it is not differentiable. But it also means that the derivative, if you can give sense to it, is the derivative of Holder 1/2, so it's slightly less than 1/2, so it's slightly less than c to the minus 1/2. And therefore, forgetting a moment about what sigma of x would be, what you have is a product of a Holder slightly less than 1/2 function with a derivative of such function, which is slightly less than minus 1/2. And if you do the dimension computation, this just fails to be integrable. The product just fails to be integrable. So you cannot give directly sense to the equation in the top. And a step to do that was done by Ito, who introduced a theory of stochastic integrals, which actually told you how exactly to do that. So you can give a sense to this integral by a construction that I will not describe at all to you. And a key point in Ito's approach is that you cannot give sense to every path W that arise, but only in a probabilistic sense, namely to almost every path W. So you cannot take any almost Holder 1/2 function and stick it into the equation and hope that something will come out. Now, as I pointed out in the beginning, you would like the property that if you approximate the noise, the solution also gets approximated. So here I gave you what is an example of such approximation. You take your noise, you integrate it against an approximate delta function. So this gives you an object NT epsilon. This is now a smooth, nice function. So you can give classical sense to the system E epsilon. And the question, is it true that that converges to the stochastic equation I defined to you earlier? And the answer is no. There is a correction term. If you look at it in the Ito point of view, there is a correction term. But since we know to compute it, this is good enough because we can understand what this means. However, remember the caveat that this is not defined for every single path W. Now, this can be somewhat, the property of continuity that I described can be somewhat generalized. And in fact, under some algebraic conditions on sigma, but not for general sigmas, the map that takes the Brownian motion to the solution of the equation I wrote is continuous. In general, however, this is not the case. And here comes the next step in the background story for ordinary differential equation, which is a deep insight of Terry Lyons about now almost 30 years ago, no, 20 years ago, sorry. And the insight was that for general diffusion coefficients, if instead of keeping track only of the path of the Brownian motion, you keep track of extra quantities, in that case, some iterated integrals of the noise, you can construct a continuous map. So you only need probability theory in order to make sense of these iterations of the basic path. But once you have those, the map between this collection of objects, a finite collection of objects, and the solution of the equation is a continuous map in an appropriate sense. Okay, so that's the first part of the background, which dealt so far just with differential equations. Now, as we all know, certainly in situations where there is noise, flow, and such problems, the equations we should deal with are not differential equations, but rather partial differential equations. And if you apply the same line of reasoning as I described to you before, you would like to talk about stochastic partial differential equations, namely partial differential equations, to which you added noise. And now your solutions are not indexed by time, but rather by time and space. So the noise should also have time and space in its index, in general. Of course, you could think of situations where the noise only is indexed by time, but in general, you would like noise to be indexed by time and space. And what generalizes what I described before is mostly parabolic stochastic partial differential equations. However, there is a problem when doing that. If what you are discussing are linear equations, like the equation I wrote now on the slide. So this is a linear equation because if you replace xi by 2 xi, then the solution will also be multiplied by 2, at least if you adjust appropriately the initial conditions. So you can give a sense to this equation by just making believe that xi is just an ordinary function. And then we know how to write the solution. It's just the green function of the equation, of the heat equation, that you integrate against the noise. So at least in situations where the green function is regular enough such that you can integrate it against the noise, this makes perfect sense. Now the problem is when you start adding nonlinear terms, because the noise itself, as it was in the ODE case, is not a smooth function. It's a derivative of a smooth function, so in general you could think of it as a distribution. And if you have a nonlinear equation, you might end up having products of distribution functions. And to anybody who ever played with distribution, products of distribution functions is a bad object. It doesn't approximate well, etc. In some cases, you can weasel your way around that, and that has more or less been the status of the theory before Martin's work. And what I want to emphasize is that Martin's theory applies to a class of equations which are considered harder in the sense that you cannot weasel your way and you have to really work with, to understand what it means to make a product of distributions. So I want to mention a representative example because this is maybe so far the most, certainly it was a spectacular result that put this method and this beginning of theory on the radar, which is a KPZ equation. So I wrote the equation for you on the board. I don't expect you to absorb it. The term in red is exactly the term I was talking about. It will turn out that the derivative of H is a distribution, so squaring it is the problematic term. The xi over there is a space-time noise that I described before. In parentheses, there are two types of KPZ running around in mathematical physics. This is a Kardar-Parisi-Zhang KPZ. Okay. So before I tell you about Martin's work, why should anybody care about this equation? So there is a fantastic side story here, which really has nothing to do with Martin's work, but I am compelled to tell you that. It models, this equation models, it was invented, and it models evolution of interfaces. And in fact, this is an example of an equation where, in a sense, you can weasel your way around. Namely, if you formally write a transformation of the solution, then what you get is an equation which is, again, a linear equation in U. The so-called stochastic heat equation, for which it's much easier to build solutions. So you can give a sense to the solution of the equation above by saying, well, let's solve the stochastic heat equation, take the log, and we will get a solution of the KPZ. Of course, this is cheating, because what you would really like to do is to take the equation on the top of the page, approximate the noise, and understand what is going on. And this will not survive. It's not clear how it survives this procedure. But what was shown actually quite a while ago, 20 years ago, is that certain stochastic systems, if you look at their interfaces, they converge after a scaling to the solution of the stochastic heat equation. So we had a microscopic system that had this equation as its limit. So that's already a good sign. If you are doing a system that is supposed to approximate reality, and you can get to it by a limit of basic microscopic quantities, you are in good shape. But what is even more amazing, and turned out to be the case in recent years, is that under appropriate boundary conditions that I will not describe here, if you analyze the properties of the fluctuations of the stochastic heat equations, you find fluctuations that are similar, actually converge to the fluctuations that you find in random metric theory. For reasons that are quite mysterious, now better understood, and I refer you to the talks of both Alexei Borodin and Ivan Korvin for glimpses of this beautiful view. And just to convince you that, that this really is something you can measure, this is an example of an experiment in which growth from a nucleus has been started. So the left picture is when you start from a single particle and you start depositing particles. The different colors represent time. The right picture, excuse me, the right picture describes evolution from a strata, from an interface, again with depositing of particles. And here are graphs that compare the experimental results now, not the theoretical, but the experimental results to what you get from fluctuations for the so-called Gaussian unitary ensemble and Gaussian orthonormal ensemble of random metric theory. And to high precision, there is a perfect fit between these two models. So this shows that understanding KPZ is interesting. So now is the time to describe to you Heirer's work. After I told you what is the background and why is it interesting to do so, excuse me, so here is a theorem. So you start with a KPZ equation, no transformation. This is not the stochastic heat equation, it's just the KPZ as I defined it before. The problem, as I mentioned, and I recall, solutions are not smooth, so you get products of distribution, so how to make sense of that? And the challenge is to give an intrinsic meaning to this equation, not to do a transformation and give an intrinsic meaning to another equation, but just this equation, and to understand how it behaves under approximation. So here is Martin's first theorem in that direction. Whoa. So suppose you take a sequence of modifications in the sense I gave before of the white noise. So you integrate the white noise against the white noise in time and space against an approximate Dirac. Then there exists constants C epsilon that you can compute as a function of your modification, such that if you take the approximate equation written up there, then solutions, first of all, exist. That's not very hard to understand, because everything now is classical. But what is more interesting is that the solutions to this approximate equation converge as epsilon goes to 0 to the solutions to something, and that something can be taken as the solution of the top equation. Okay. Now, of course, if that is the situation, you can take this limit of approximations, which does not depend on the particular approximation, as the definition of the solution above. The constant C epsilon, which will come about from a normalization procedure, actually depends on the modifier, but the limit does not, which is another desirable feature we had in our list of features. The convergence in general as distribution, in this case, is actually better. It's in the sense of Holder functions. But what is more important is that the point of view taken in this work and later in the work on regularity structure introduces a completely new setup that allows you to look at many different such equations and to try to make sense of them. And the insight that I want to emphasize here is that you do not try to directly solve the equation or whatever. You're trying to construct something similar to Taylor expansion, except that you are going to use expansions that are tailored to the equation you are trying to solve. So you look at the equation you are trying to solve, and you try to construct a replacement for polynomials, which is what we do in Taylor expansions. And then you are trying to do that in a way that is consistent in epsilon. So what do I mean? What do I mean by that? So first of all, I already showed you in the context of finite dimensional example, in the case of ODEs, one such approach, which was Lyon's approach. Lyons told us, well, what you can do is instead of looking just at the path of the Brownian motion, if you keep track of the Brownian motion and its iterated integrals, together you can reconstruct the solution based on those. Heirer tells us, no, you shouldn't do that because this works for all equations at once, and this is not what is going to happen here. Instead, you should look at local expansions in some kind of multilinear forms of the noise and write the solution in terms of those. Now, there is one desirable property that somehow when we change epsilon, the solutions should go one to the other. So you should be able to link the solutions one to the other. And this is done by a renormalization procedure. The normalization procedure is taking care of only finite number of terms in the expansion, and and by doing that, you can reconstruct the solution. So to give a little bit more insight, I will show you an example of how the calculation actually goes, but to give you a little bit more insight, let us recall what you do when you have a Taylor theorem. So when you take a function, a smooth function, you can expand it as a Taylor series. Now, we always think of a Taylor series as a series that allows us to define the function to arbitrary precision in a neighborhood of a point. And in particular, if, for example, the function is analytic, you can just, from it, describe the whole function everywhere. But the point is, and this is such a triviality that it sounds surprising that it would be useful, is that in fact, if you have a Taylor expansion, in order to reconstruct the function, you can forget about the expansion. The first term is a value at a point. So if you compute something like a Taylor expansion, and all your goal is to compute the value of f, all you have to keep track is one coefficient at each point, the first coefficient, f of z0. So what Heirer does, he attaches at each point in space-time a linear space of abstract elements of given homogeneity, together with a transfer rule between points and a map to distributions. This is something that he calls a model. And the solution is determined just by the negative homogeneity coefficient of the expansion and the basis element. Remember, the basis element are equation specific. They are not the same for different equations. Of course, as I describe it here, different epsilons give different models. So what you need to do is to glue somehow these models in a continuous way that preserves all the nice algebraic features we wanted of the problem. And this is a renormalization procedure that I was alluding to before. So when you want to glue together solutions for different epsilons, you can do that if you allow an appropriate renormalization, which in this case means just a linear transformation between basis elements. And a priori, it is not at all clear that you can do that. There is no reason to expect before you start dirtying your hands that you could do that. What Heirer does, it proves the fact that A, you can do that, and B, you can characterize the possible linear transformations that will preserve these nice algebraic structures. And this collection, as I said, is what is called the regularity structure. I would like to just quickly show you how the computation goes without explaining in details what is going on. So this is a KPZ example. There are some basic operations. If we didn't have the quadratic terms there, then we know that a convolution with a green function would be important. So Heirer, who is also a very talented programmer and has other talents that I let you read over the internet, he invented a graphical language for bookkeeping of these transformations, which will look familiar to people who are versed in techniques of diagrammatic expansion in math physics, but that somehow in this context look surprising. So there are some objects, for example, convolution with green function is important. We saw that this is important already in the linear case. Differentiation is certainly important because we want to be able to talk about the derivative of h. So this he represents by a straight line. The basic element is the noise, which he represents by a circle. The spatial Taylor element, the element basis, he represents by x. And then he can write the operator, which is the formal solution of the equation above, as an integral of applying the derivative of the solution twice, plus the noise, and integrating against the green function. So this is what is written here. You can open it up. You see a little element, this little wiggle on the right side, which is just the effect of applying the green function on the noise. And you can start iterating that. And as you iterate, you get this fancy diagram that tells you you get this wiggle object and then noises that will get multiplied and then integrated, etc., etc. So here is an example of an extra iteration. And now comes the renormalization I was talking about. So the renormalization is just a linear operator on the basis elements. It's an exponent, and Martin's theorem is that you can rewrite it in this way. And these basis elements has the effect of contraction. So they can contract complicated diagrams to simple ones. So for example, you have this kind of relations. And what you would like, if everything should work well, you would like to have that renormalizing the equation would be the same as renormalizing inside plus corrections, which are nice smooth functions. And when you use that as a constraint, you get that the correction part, the low homogeneity correction part, is what is written over there. It turns out in the case of KPZ that the C0 term is 0. That's why in the equation I wrote, you never had a derivative of the equation, and then a bunch of constants which collectively together give you the C epsilon I had in the main theorem before. So I'm certainly not explaining how you get all these. You are welcome to Martin's talk, but this is something that came out of the blue. This point of view of looking at equations in this way came, I think it's fair to say, as a complete surprise for people. People have been looking at stochastic differential equations for quite some time and dealing with nonlinear equations at least for the last 20 years. And very little has been done in the context of this hard work. I should mention that recently there have been work by other people that propose related and different approaches, but none of those has a far-reaching panorama that this one gives us. So let me summarize. What was introduced here is a completely new methodology for defining solutions of partial differential equations driven by rough noise. I tried to explain you why those are important. The method is robust, inherently robust with respect to modifications. It gives you some quantitative estimates on the solutions. And now, of course, the Fields Medal is given not only about past work, but also about future potential. So I thought I'll close this by some future potentials that we are all eagerly waiting to hear about. The first thing is that right now, the theory is somewhat limited in that it deals with compact domains. And one would like to deal with unbounded domains. The main reason is that there is a big difference when you're dealing with large time behavior between compact domain and infinite domain, and large time behavior is very much of interest. For example, in the deposition problems I discussed, of course, since you start from a microscopic problem, you have to look at some rescaling before you start seeing something. There are some notions of universality that in the world of integrable systems that I described before have already made appearance, and one would like to have a theory, and there are now several initial steps already in this direction. You would like to understand convergence for a general microscopic model to renormalized equations in more generalities than is available right now. And of course, the question mark is the most important of all. Thank you for your attention, and congratulations, Martin, for this beautiful work.